Every time you see a rocket launch, you're watching it write a story. It's this brilliant, fiery epic of power and propulsion. But here's the thing. The most important part of that story is completely invisible. It's a message written not in light, but in heat. And learning to read it is a total game changer.
You see, that blazing column of fire isn't just exhaust. It's radiating a crazy amount of heat, creating this unique signature in the infrared spectrum. This invisible light is basically a fingerprint, and it tells a surprisingly detailed story about the rocket itself.
And that's the billion-dollar question, isn't it? For engineers, for defense analysts, for pretty much everyone in the aerospace world. How in the world do you decode a message that's written in invisible light? Well, that's exactly what we're about to dive into. Okay, so first things first, we need to get a handle on what exactly we're looking for. This isn't just about seeing heat. It's about reading a very, very specific pattern.
This right here is the core concept, the infrared or IR signature. Think of it like this. The superheated gas in that exhaust plume gives off a unique pattern of heat. And just like a fingerprint, no two rocket designs have the exact same one. It's all about the mix of temperature, chemicals, and pressure.
So why does this fingerprint matter so much? Well, for defense systems, it's literally everything. That's how you spot, track, and figure out what kind of missile is coming at you. But for rocket designers, it's the complete opposite. Their goal is to shrink that signature to make their vehicle as stealthy as possible. It is a super high-stakes game of hide and seek.
So to figure out how to either hide this signature or get better at finding it, you first have to understand what creates it. So let's get into the science and see how researchers are cracking this code. And this is where it gets really cool. A study published in the Chinese Journal of Aeronautics did exactly that. Researchers built this incredibly powerful digital model, an infrared signature analysis tool, to simulate a rocket's plume in insane detail and figure out what makes its invisible signature tick. And what they did was zero in on 3 key variables that they thought had a huge impact on that IR signature. This thing called afterburning, the wild pressure swings inside the engine, and even tiny, tiny changes to the rocket fuel itself.
Okay, let's tackle that first one, which is this surprisingly powerful phenomenon called afterburning.
All right, check this out. On the left, you've got a simplified model where unburnt fuel just kind of exits the nozzle and cools down. But the reality, on the right, is way more dramatic. See, most rocket fuel is designed to be fuel-rich, so all that superheated, unburnt gas slams into the oxygen in the atmosphere and bam, it reignites. That is afterburning. And the effect is just stunning. The research found that this secondary burn doesn't just make the plume a little bit hotter, it can boost its infrared brightness by a massive 40%. I mean, that is a huge leap in visibility. That could easily be the difference between being seen and staying hidden. So the bottom line is simple. Afterburning is like a giant amplifier. It makes the rocket's invisible fingerprint bigger, bolder, and way, way easier to spot from a distance. All right, next up. The researchers took a look inside the rocket motor itself, at the immense and constantly changing pressure. You know, a rocket firing isn't some smooth, steady burn. It's violent. As you can see on this timeline, there are these huge pressure spikes right at ignition and then again just before the engine shuts down. And these are not minor little bumps. They fundamentally change the exhaust. So what happens when the pressure goes nuts like that? It totally changes the plume structure. It forces the exhaust out with way more energy, creating those beautiful shock diamonds you sometimes see. But here's the kicker. Those same patterns exist in the invisible infrared spectrum, creating a really distinct pulse of energy. In fact, the link is so direct, so predictable, that the researchers basically concluded you can map the plume's infrared brightness directly to the pressure inside the engine. When the pressure spikes, the IR signature flares right along with it. It's that simple. Okay, this last one. This is the one that really blew my mind. It turns out that tiny, almost insignificant seeming changes to the fuel's recipe can have enormous consequences. So the researchers were looking at this super common solid propellant. It's basically made of a fuel binder, called HTPB, and an oxidizer, AP. They decided to focus on the precise ratio between these two main ingredients, the fundamental recipe of the fuel. And they made a really small adjustment. In their computer models, they just shifted the balance between the fuel and the oxidizer by only 3%, just a tiny tweak in the grand scheme of things.
I mean, come on, 3%. How much of a difference could that really make, right? It sounds like it would just get lost in the noise of such a violent explosion.
Well, get this. The result was absolutely astonishing. That tiny 3% change in the recipe caused the brightness of the IR signature to jump by 50% in certain key infrared bands. 50%! That's not a small tweak. That's like flipping a switch from a candle to a searchlight. A massive change from a microscopic adjustment.
So, when you put all of this together, the afterburning, the pressure, the fuel mix, what does it actually mean out there in the real world? Well, each of these things is a lever that can be pulled in a very high-stakes game.
And this brings us right back to that game. On one side, engineers can now use this knowledge to design engines and fuels that create a fainter, cooler signature to make things stealthier. But on the other side, sensor designers are using the exact same information to build systems that are more and more sensitive to those exact telltale signs.
By cracking the code of the plume, we've basically kicked off an arms race in the infrared spectrum. One side gets better at hiding, the other gets better at seeking. And it leaves us with a pretty fascinating question. In a battle fought with invisible light, who's ultimately going to win?